In this case, we have this magnet. This magnet has a north pole and a south pole, and we have a current carrying conductor, which is a wire with some current flowing through it. These magnetic lines of force are going to be completely different from each other. The current carrying conductor is just like over here. We use a right-hand rule. We put our thumb in the direction of that conventional current moving, and then our fingers wrap around this current carrying conductor and tell us that there are concentric lines of magnetic flux going around this current carrying conductor in this direction, all in this direction, and they get more and more spread out as the magnetic field gets weaker and weaker away from the current carrying conductor. But that's different than a piece of ferromagnetic material sitting on my desk that doesn't have current going through it. That follows the classic definitions of magnetism that say that magnetic flux lines travel from the North Pole to the South Pole and through the material, from the North Pole to the South Pole through the material again, getting weaker and weaker in free space as they repel one another and getting more and more dense towards the poles. So when we look at our magnetic flux lines from a ferromagnetic material by itself compared to a current carrying conductor, they are very, very different from one another. There are no poles in the situation of a current carrying conductor. There are poles. This is North Pole. There's a South Pole here, and the magnetism is getting concentrated near the poles. So when we separate these two concepts, we see that the magnetic flux lines are both present, but they are present in very, very different ways. And what becomes really useful is when we join them together.